viewers, this is 4th lecture on linear algebra. In earlier 3 lectures we have discussed vector spaces, subspaces and bases. Today's lecture has direct sum, complementary subspaces, ordered bases and change of bases. I will start with few definitions. The first is the sum of two subsets S1 and S2 of a vector space V. So, if we have two subsets S1 and S2 of a vector space V, then the sum of S1 and S2 is defined as S1 plus S2 equal to alpha plus beta, such that alpha belongs to S1 and beta belongs to S2. So, the set S1 plus S2 consists of all vectors of the form alpha plus beta in the vector space V, such that alpha belongs to S1 and beta belongs to S2. For example, if we consider S1 as a set consisting of 1 and 1, comma 0 and 1, clearly this is a subset of R2, and another subset S2 consisting of two vectors 1 0 and minus 1 1. These two belongs to this also is a subset of R2. One may notice that R2 is a vector space. Now, the sum S1 plus S2 consists of sum of these two sets S1 and S2. So, to form a sum I have to take a vector from this and a vector from the set S2. So, 1 comma 1 from S1 and 1 0 from S2, then 1 comma 1 from S1 and minus 1 comma 1 from S2, 0 1 from S1 and 1 0 from S2, finally 0 1 and minus 1 minus 1. You simplify it, it is 2 1 0 2 1 1 and minus 1 0. So, S1 plus S2 consists of the vectors of this. Then the next is the theorem. If W1 and W2 are subspaces of V, then the sum W is equal to W1 plus W2 is also a subspace, and W1 plus W2 is equal to span of W1 union W2. Now, to prove this, I will first prove that W is equal to W1 plus W2. So, to prove this, let alpha beta belongs to W. Then, since W is W1 plus W2, so this alpha can be written as alpha 1 plus alpha 2, alpha 1 belonging to W1 and alpha 2 belonging to W2. Beta also belongs to W, so this can also be written as beta 1 plus beta 2, beta 1 belonging to W1, beta 2 belonging to W2. So, their linear combination C alpha 1 plus alpha 2 plus beta 1 plus beta 2 must also belong to W1 plus W2, only then W1 plus W2 is a subspace. So, I write C times alpha 1 plus alpha 2 plus beta 1 plus beta 2 is equal to, simplifying it, it is still C alpha 1 plus beta 1 plus C alpha 2 plus beta 2, but alpha 1 belongs to W1, beta 1 belong to W1 and W1 is a subspace. So, C alpha 1 plus beta 1 belongs to W1 and C alpha 2 plus beta 2 linear combination of two vectors of W2, W2 being a subspace. So, this also belongs to W2. So, what we can say is that C alpha plus beta also belongs to W, because the right hand side can be written as sum of vectors, one from W1, another from W2. And this proves that W1 plus W2 is a subspace. Now, the next part we have to prove that W1 plus W2 is equal to span of W1 union W2. So, this again I prove in two parts. First, I will show that S span of W1 union W2 is contained in W1 plus W2, and later on I will show that W1 plus W2 is a subset of span of W1 union W2, and that proves this equality. So, to prove the first part, I consider the span of W1 union W2. So, let us say we have a vector W in span of W1 union W2, then this can be written as a linear combination of vectors of W1 union W2. So, what are the vectors of W1 union W2? They will be vectors belonging to W1 and vectors belonging to W2. So, I write W as C1 alpha 1 plus C2 alpha 2 plus Cn alpha n plus D1 beta 1 plus D2 beta 2 plus Dm beta m. The idea is that alpha 1, alpha 2, alpha n, they belongs to W1 and remaining vectors they belong to W2. So, if these belongs to W1, then beta 1, beta 2, beta m, they belongs to W2 because they are from the set W1 union W2. So, now we write down this part which is consisting of vectors of W1. So, linear combination of vectors of W1. So, C1 alpha 1 plus C2 alpha 2 plus Cn alpha n must belongs to W1 because linear combination also belongs to W1 being a subspace. Similarly, this is a linear combination of vectors of W2. So, W2 being a subspace. So, beta equal to D1 beta 1 plus D2 beta 2 plus Dm beta m must belong to W2, and that means W can be expressed as a vector from the set W1 and a vector from the set W2, and that means W is equal to, that means W belongs to W1 plus W2. So, first part is proved. The second part is that any vector in this set W1 plus W2 is also in the set which is the span of W1 union W2. So, if W belongs to W1 plus W2, then we will prove that this also belongs to this, and that means this is this, and W1 plus W2 is a subset of SW1 union W2. So, I start with W belonging to W1 plus W2. Since W1 plus W2, this implies W belongs to span of W1 union W2. Now, alpha is linear combination of these vectors and they belong to W1, beta is linear combination of vectors of W2. So, they also belongs to W2 because they are subspaces, and then alpha plus beta is C1 alpha 1 plus C2 alpha 2 plus Cn alpha n, and D1 beta 1 plus D2 beta 2 plus Dm beta m. So, the sum of these two is alpha plus beta. Now, what is this? This is a linear combination of vectors of W1 union W2. So, definitely this must be in the span of SW1 union W2. So, W1 plus W2 is a subset of span of W1 union W2, or combining the two things, what we can say is that W1 plus W2 is equal to span of W1 union W2. Now, we define direct sum. The vector space V is said to be the direct sum of its subspaces S and T, and we denote it by V is equal to S plus T. Now, here we are using a different symbol than plus just to differentiate between the sum and the direct sum. So, V is equal to S plus T if every vector V belonging to V can be written in only one way as V is equal to U plus W, where U belongs to S and W belongs to T. Now, we state a theorem. According to this, the vector space V is the direct sum of subspaces S and T if and only if V is equal to S plus T and S intersection T is equal to null vector 0. Now, the basic difference between direct sum and sum is that while we can express V as S plus T, sum of S and T, here we have this representation is unique, and this is guaranteed by S intersection T is equal to 0. So, let us try to prove this. Suppose V is equal to S plus T, then any vector V belonging to V can be uniquely written in the form V is equal to U plus W, U belonging to S and W belonging to T. That means V is equal to S plus T. Now, you have to show that if it is uniquely represented by the definition of direct sum, then this means S intersection T is equal to 0. So, if V belongs to S, then we can write down V is equal to V plus 0, 0 belonging to T and V belonging to S. So, now it is the sum of two vectors, one from S, another from T. So, V belongs to V. Similarly, if V belongs to T, then we can write down V is equal to 0 plus V, the null vector from the set S and V in T. So, this V will also belongs to V. So, now we have two representation for the same vector in V. Now, this is possible only when S intersection T is equal to 0. Since V has a unique representation, so this has to be 0. Otherwise, we will be having two different representations against our assumption that it is a direct sum. So, S intersection T has to be a null vector. Now, in the second case, we assume that V is equal to S plus T and S intersection T is equal to 0, then we say that this representation will be unique and this plus will now be not be the sum, but the direct sum. So, we start with this and we prove that V is the direct sum of S plus T. Now, to do this, let V belongs to V is expressed as V is equal to U plus W, U belonging to S and W belonging to T. At the same time, the same vector V can also be expressed as U dash plus W dash, where U dash belonging to S and W dash belonging to T. So, since the two vectors are same, so I can write down U plus W is equal to U dash plus W dash, or I can simplify U minus U dash is equal to W dash minus W. Now, U minus U dash belongs to S and W dash minus W belongs to T and they are equal. Now, since S intersection T is equal to 0 vector, so this is they are equal only when the U minus U dash is 0 and W dash minus W is equal to 0, and that means S intersection T is equal to 0. So, since U minus U dash is 0 implies U is equal to U dash and W dash minus W is equal to 0 implies W dash is equal to W. So, we have started with two different representations for the same vector, but ultimately we arrived at the unique representation, and that means V is equal to S plus T and S intersection T is equal to null vector actually means that a vector can be expressed uniquely in V, and that means that it is not sum, it is the direct sum. So, this can be used as a definition for direct sum also. The next theorem says that if U and W be finite dimensional subspaces of vector space V, then dimension of U plus dimension of W is equal to dimension of U plus W plus dimension of U intersection W. This is an important result. Let us try to prove this. Now, U and W be finite dimensional subspaces. So, let us say basis for U is m dimensional and it is U1, U2, Um, and basis for W is W1, W2, Wn, n being the dimension for W. Let U intersection W is R dimensional subspace and its basis is S is equal to V1, V2, Vr, it is sum only. So, we can consider U intersection W as finite R dimensional subspace, and let us say its basis is V1, V2, Vr. Now, since it is intersection, so these vectors belongs to U also, this is basis, so these vectors will be independent. These vectors belongs to W also. So, let us say we can extend this basis to form a basis for U, but U is m dimensional. So, let us add m minus r vectors in B1. So, B1 becomes V1, V2, Vr, U1, U2, Um minus r. So, the total number of vectors are m. So, we have a basis for U. Similarly, we can form a basis for W, we call it B2. So, we have same basis V1, V2, Vr, and then we add n minus r vectors, independent vectors, so that this forms a basis for W. Then we consider B is equal to B1 union B2. So, we have two bases. So, we consider B is equal to B1 union B2. So, how many vectors will be there? We will be having V1, V2, Vr vectors, then U1, U2 up to Um minus r, and W1, W2 n minus r. So, union of B1 union B2 will be this set, and it will definitely have m plus n minus r elements, and it generates U plus W. If the set B is independent, then it will form a basis for U plus W subspace. So, we have to prove that these has independent vectors. So, for this we consider the linear combination of these vectors. So, the combination is C1 V1 plus C2 V2 plus CR Vr, then we will have plus C1 dash U1 plus C2 dash U2 plus Cm minus R dash Um minus R, plus D1 W1 plus D2 W2, and the last is Dn minus R Wn minus R equal to 0. So, we have formed the linear combination of vectors of B. Since B1 is a basis for U, therefore, for some U belonging to U, we have U is equal to C1 V1 plus C2 V2 plus CR Vr, this plus this C1 dash U1 plus C2 dash C2 plus Cm minus R dash Um minus R. So, this will be a vector belonging to U. Similarly, if we substitute this, then we can write down U is equal to minus D1 W1 plus D2 W2 plus Dn minus R Wn minus R. So, this is a vector which is U, and this I have taken on the other side. Now, since the vector on the right belong to W, so U belonging to U intersection W, that is U can be expressed as a linear combination of vectors of V1, V2, Vr, that is U is equal to D1 dash V1 plus D2 dash V2 plus Dr dash Vr. Substitution in 2 gives us D1 dash V1 plus D2 dash V2 plus Dr dash Vr plus D1 W1 plus D2 W2 plus Dn minus R Wn minus R is equal to 0. However, V1, V2, Vr, W1, W2, Wn minus R is the basis for W, and therefore, D1 dash D2 dash Dr dash is equal to D1 is equal to D2 is equal to Dn minus R has to be 0, and substitution in 1 gives C1 V1 plus C2 V2 plus C1 dash U1 plus C2 dash U2 plus Cm minus R dash Um minus R is equal to 0, and since this forms a basis for the set, then C1 is equal to C2 is equal to Cn is equal to C1 dash is equal to C2 dash, and that means all coefficients are 0, and that means all the vectors are linearly independent. Hence, B is a basis for U plus W, and this means dimension of U plus W is equal to m plus n minus R, where dimension of U is equal to m and dimension of W is equal to n. So, starting with dimension is equal to U plus W is equal to m plus n minus R, and dimension of U is equal to m and dimension of W is equal to n. Further, dimension of U intersection W is equal to R. So, if we substitute these things in this result, then we will have dimension of U plus W is equal to dimension of U plus dimension of W minus dimension of U intersection W, and this proves the result that dimension of u plus dimension of w is equal to dimension of u plus w plus dimension of u intersection w. We have taken this on the other side. So, this is an important result and will be useful in many different ways. Now, we take up some examples. So, let us consider two subspaces of R 4. Now, R 4 is a vector space and it has dimension 4. So, let us consider V as A, B, C, D such that they follow a constraint A minus C plus D is equal to 0, where A, B, C, D they are real numbers. The other subspace W is equal to A, B, C, D following this constraint A is equal to B and C is equal to D. So, the question is find the basis and dimension of V W and V intersection W. So, we start with the solution. Clearly, the dimension of V cannot be 4. So, we start with a set B1 consisting of 0 1 0 0 and 0 0 1 1 1 0 1 0, a set of 3 vectors. We claim that any vector of V can be generated by B. So, this is the span for V. So, for this purpose we consider A, B, C, D in V satisfying the given constraint A minus C plus D equal to 0. So, we express this vector A, B, C, D in V as a linear combination of vectors of the given set. So, it is alpha times 0 1 0 0 first vector plus beta times second vector plus gamma times third vector. So, if we combine these terms, then A, B, C, D is equal to gamma plus alpha, beta plus gamma and finally beta. Now, comparison gives gamma is equal to A, alpha is equal to B, C is equal to beta plus gamma and beta is equal to D. Now, C is also A plus D from this constraint. So, I have combined this constraint and what I am getting from here, and if you solve them, then alpha is equal to B, beta is equal to D and gamma is equal to A. So, these are the 3 coefficients alpha, beta, gamma. So, I have solved them using this. So, any vector A, B, C, D can be expressed in this form. Now, the vectors of B1 are independent, that can be checked, and since the vectors of B1 spans spans the subspace V, therefore, we say that B1 forms a basis for V, and since there are 3 independent vectors in B1, so dimension of V is 3. Now, if we consider the another subspace W satisfying this constraint A is equal to B and C is equal to D. So, we start with a set B2 consisting of 1 1 0 0 and 0 0 1 1. There are 2 constraints. So, we start with a set of 2 vectors and let us see whether they form a basis for this subspace or not. So, any vector in W which is of this form can be obtained as a linear combination of vectors of B2. So, I leave this in exercise for the viewers to satisfy, and further the vectors of B2 are independent. So, again they can check whether these 2 vectors are independent or not. So, if this spans the vector space and vectors are independent, then the B2 will form a basis for W, and in that case the dimension will be 2 because there are only 2 vectors in the basis. Now, V intersection W, V intersection W is the set of vectors A, B, C, D which satisfy both the constraints on V and this is the constraint on W. Now, V is equal to A, B, C, D, any vector which belongs to V intersection W, then these constraints should be satisfied. So, A minus C plus D is equal to 0, A is equal to B and C is equal to D, and this means A is equal to 0, A and B both are 0 and C is equal to D. So, dimension of V plus W is equal to dimension of V plus dimension of W minus dimension of V intersection W. So, this is 3, we have already proved dimension of V as 3, the dimension of W is proved to be 2 and dimension of V intersection W we have just now proved it to be 1. So, it is 5 minus 1 is equal to 4 and that means V plus W is a 4-dimensional vector space. Now, R4 is also a 4-dimensional vector space and in fact, we say that V plus W is equal to R4. Now, this is the next example. Consider the 3 subspaces of R cube as U, V, W defined by this set A, B, C satisfying this constraint for A, B, C belonging to real set. V is equal to A, B, C, A is equal to C. This is the constraint on this vector subspace and W is equal to 0, 0, C and C belonging to R. Now, we have to show that R cube is the direct sum of V and W while R cube is not the direct sum of U and V. So, the solution, we consider x, y, z belonging to R cube and we prove that any vector in this can be written as U as V plus W, that is the first part. So, let us say 0, 0, z minus x belongs to W. W is of the form 0, 0, c. So, I will take the c as z minus x belonging to W and the vector V is when A and C components are equal. So, I will take this vector from V as x, y, x. So, if I add the two vectors x, y, x from V and 0, 0, z minus x from W, then x, y, z can be expressed as sum of these two vectors and that means R cube is equal to V plus W. But this does not prove that R cube is a sum of V plus W, but it does not mean that it is direct sum. To prove that it is a direct sum, we have to prove that V intersection W is equal to 0. So, one can notice that this V plus W equal to 0 only when Z is equal to only when the intersection of the two is equal to 0. So, this can be easily seen from the way we have chosen the vectors and that is why we can say that V intersection W is equal to null vector or R cube is direct sum of V and W. Now, in the second part we assume that R cube is equal to U plus V. That means C1, C2, C3 belongs to U satisfying the constraint C1 plus C2 plus C3 equal to 0 and alpha beta alpha belonging to V. That means the vector x, y, z in R cube can be expressed as sum of these two vectors C1, C2, C3 plus alpha beta alpha. And if we compare, then x is equal to C1 plus alpha, y is equal to C2 plus beta, z is equal to C3 plus alpha, and that means x plus y plus z is equal to C1 plus C2 plus C3 is equal to 2 alpha plus beta, and since C1 plus C2 plus C3 is equal to 0, that means x plus y plus z is equal to 2 alpha plus beta. And from here we can express alpha as x plus y plus z minus beta by 2. We can solve these equations again for C1. So, twice C1 is equal to 2x minus x plus y plus z minus beta, or x minus y minus z plus beta. Similarly, for C3 the solution is z minus x minus y plus beta, and C2 is equal to y minus beta. So, this is the vector x minus y minus z plus beta by 2 comma y minus beta comma z minus x minus y plus beta by 2 belongs to U, and V belongs, and alpha beta alpha belongs to V. Then R cube can be written as U plus V. So, R cube is sum of U plus V, but it is not a direct sum. In fact, this sum has two independent constants alpha and beta. So, changing the values of alpha and beta, you can express R cube in many different ways. So, it is not a unique representation, and that is why although R cube is sum of U and V, but it is not the direct sum of U and V. In fact, one can further prove that U intersection V will be a set of the form minus beta by 2, beta minus beta by 2, and beta belongs to R, and this will be 0 only when beta is equal to 0, but beta can take any value, and U intersection V will be a set of this form, because it has to satisfy two constraints, alpha and the first and last components equal, and sum of the components equal to 0, and that is why U intersection V is not the singleton 0. So, hence R cube is not the direct sum of U and V. So, in this example we have three sets. R cube is a direct sum of first and third, but it is not the direct sum of U and V, the first two. Now, in the next example, if V be the vector space of square matrices of order n over a field R, and U and W be the subspaces of symmetric and skew symmetric matrices respectively, then we have to show that V is the direct sum of U and W. And we have already proved that square matrices form a vector space, and U is the set of symmetric matrices, they form a vector space or a subspace of this vector space V, and W, the set of skew symmetric matrices, also forms a subspace. Now, we have to show that V is the sum of U and W. Now, to prove this, we first observe that every square matrix A in V can be expressed as sum of a symmetric and a skew symmetric matrix, and that means we can in fact manipulate A as half A plus A dash A transpose plus half A minus A dash. In this we have established that A plus A dash is symmetric, while the matrix A minus A dash is skew symmetric. So, matrix A in V can be expressed as a sum of symmetric and skew symmetric matrix. So, we can say that V can be expressed as sum of symmetric matrices and skew symmetric matrices. Now, this will be the direct sum provided their intersection is empty, their intersection is null matrix. So, to prove that U intersection W, if we say U is the set of symmetric matrices and W is the set of skew symmetric matrices, then we have to prove that this is nothing but the null matrix. So, let us say M belonging to U intersection W, any matrix M belonging to U intersection W, then M has to be symmetric matrix, but because it belongs to this intersection, and M belongs to V also, where V is skew symmetric. So, M belonging to skew symmetric matrices. Now, the two have, this is possible, the matrix is symmetric as well as skew symmetric. This is possible only when U intersection W is theta, and that means V is direct sum of U plus W. This is what is to be proved. So, I have taken an example from matrices. Now, this is another example. that U and W be subspaces of R cube for which dimension U is 2 and dimension W is 1, and W is not a subset of U, then you have to show that R cube is equal to U plus W. Now, since W is not contained in U, so U intersection W, there is nothing common between W and U. So, W intersection U, and they are subspaces. So, definitely this null vector has to be there. So, U intersection W is this. So, dimension of U intersection W is 0. Now, dimension for U plus W is equal to dimension of U plus dimension of V, dimension of U being 2, dimension of V being 3. So, dimension of U and W are subspaces of R cube. Now, R cube is direct sum of U and W. So, R cube is U plus W. Now, with this we come to another topic, that is complementary subspaces. So, first we define complementary subspaces, that according to the definition, let S be a subspace of a vector space V, then subspace T is said to be complementary subspace of S if it can be expressed as V is equal to direct sum of S and T. Trivially, the subspace 0 and V have unique complementary subspaces, V plus 0 is equal to V. The complementary subspace of 0 is V and the complementary subspace of V is 0. Let us illustrate this with example. So, let us consider U as A B C satisfying the constraint A plus B plus C equal to 0, A B C belonging to R and it is a subspace. Similarly, W is equal to 0 0 C, C belonging to R, then show that U is complementary subspace of W. This we have already done in one of the earlier exercises. Any vector x y z in R cube is written as sum of U and sum of W, sum of U belonging to U and W belonging to W, then x y z is equal to A B C plus 0 0 D, where the constraint A plus B plus C is equal to 0. Now, comparing the components, then A is equal to x, y is equal to b, z is equal to c plus d and c is equal to minus x minus y from this, and x comma y comma minus x minus y. So, that x plus y plus z equal to 0 plus 0 0 comma z plus x plus y. So, that way we can express x y z as a combination of a vector from U and a vector from W. Now, we consider A B C belonging to U intersection W. Now, if A B C belongs to U, then A plus B plus C equal to 0, and if A B C belongs to W, then A has to be 0 and that means B has to be 0 and also C has to be 0, and that means U intersection W is simply a null vector. Now, this simply means that U is a complementary subspace of W. Generally, the complementary subspaces of a subspace is not unique. This is the observation we make in context with number of cases. Now, we come to another concept, ordered basis. So, we define if V is a finite dimensional vector space, then an ordered basis for V is a finite sequence of linearly independent vectors spanning V. So, the idea is that we have already defined basis for a vector space for a finite dimensional vector space, but to define ordered basis we have to add some sequence, some specific order, some specific ordering is to be incorporated. So, if we say let B is alpha 1 alpha 2 alpha n is an ordered basis for the vector space V, then any vector alpha in V can be expressed as a linear combination of vectors of B, that is alpha is equal to C 1 alpha 1 plus C 2 alpha 2 plus C n alpha n. Now, in this case the n-tuple C 1 C 2 C n of scalars are called the coordinates of alpha related to the ordered basis B. Now, we have a result which says that the coordinates of the vector alpha with respect to an ordered basis are unique. We prove this result by contradiction. So, let there be two coordinates of vector alpha belonging to V, and the two coordinates are C 1 C 2 C n and D 1 D 2 D n with respect to the ordered basis, such that alpha is linear combination of the vectors alpha I of the ordered basis such that alpha is equal to summation C I alpha I, and alpha can also be expressed as alpha is equal to summation D I alpha I. And the idea is that C i's and D i's are the coordinates of the vector alpha. Then since they are equal, so we can equate them, and simplifying gives summation C I minus D I into alpha I is equal to 0, and since alpha I belongs to B are independent vectors because they form a basis. So, these coefficients must be 0, and that is why C I minus D I is equal to 0 for all values of I, and this gives me C I is equal to D I, which is a contradiction, and hence there is a unique representation. You cannot have two different representations, or you cannot have two different set of coordinates of the vector alpha with respect to an ordered basis B. So, this proves the theorem. Now, let us try to find out the coordinates of a given vector with respect to given ordered basis. So, let us consider an ordered basis of R cube as 1 1 1, 1 1 0 and 1 0 0, and let us try to represent V, the vector V, which is a vector in R cube. So, it is of the form 4 3 1. So, we have to find out the coordinates of this vector 4 3 1 with respect to this ordered basis. So, we assume the coordinates of V be C 1 C 2 C 3. That means, by definition 4 3 1 is equal to C 1 times 1 1 1 the first vector plus C 2 times the second vector 1 1 0 plus C 3 times the third vector 1 0 0. So, we have to solve the system, and that amounts to 4 is equal to C 1 plus C 2 plus C 3, the first equation. This gives the second equation will be 3 is equal to C 1 plus C 2, this will not contribute, and finally 1 equal to C 1, this will not contribute, also this will not contribute. So, this equation is actually equivalent to this set of 3 equations. C 1 is equal to 1, we have already obtained. We substitute this in this equation, this gives me C 2 is equal to 2, and substituting these two values in this equation gives me C 3. So, C 1 is equal to 1, C 2 is equal to 2, C 3 is equal to 1 is the solution of this set of equations, or we can say that the coordinates of vector 4 3 1 relative to the given ordered basis are 1, 2 and 1. Now, the coordinates of this vector 4 3 1 actually are given in the natural basis or standard basis. So, a vector space R 3 can have number of bases. This is another basis for the vector space R 3. And the next example we have taken from matrices. So, let us say we have a vector space of all real square matrices of order 2. Find the basis and dimension of V and find the coordinates of the matrix 2 3 4 1 with respect to the basis. So, we will first try to find out the basis. We start with this set B is equal to B consisting of these 4 matrices 1 0 0, 1 0 0 0, 0 1 0 0, 0 0 1 0, 0 0 0 1. So, we consider set B, and then we claim that B is a set of independent vectors. For this, we consider the linear combination of these vectors A 1 0 0 plus B times the second vector plus C times the third vector plus D times the fourth vector, and this linear combination equal to 0 0 0 0, the null vector. We solve this, then A is equal to 0, B is equal to 0, from here we will have A equal to 0, from here B comes out to be 0, from here C comes out to be 0, and finally D is equal to 0. Now, we have to see that B spans V. So, we consider C1, C2, C3, C4 a 2 by 2 square matrix belonging to the vector space V, then any such square matrix of order 2 can be represented in the as a linear combination of these 4 vectors. So, then we try with this C1, C2, C3, C4 is equal to A times first vector, B times second, C times third, and lastly D times the fourth, and simplifying gives me A is equal to C1, B is equal to C2, C is equal to C3, and D is equal to C4. So, all these coefficients can be obtained in terms of the given vector. So, we can say B spans V. So, B spans V is a linear combination of independent vectors. So, we can say that B is a basis, and since B has 4 vectors in it, so dimension of V is 4. Now, the coordinates of given vector with respect to the given basis can be obtained from this relationship 2 3 4 1, A times the first vector which is given to us plus B times the second vector given to us, C times the third vector, and D times the fourth vector. So, if we solve it, it is A plus B plus D equal to 2, then second is minus B plus D minus C equals to 3, then C plus D equal to 4 and D is equal to 1. So, these are 4 equations and they can be solved simultaneously. We will have A is equal to 6, B is equal to minus 5, C is equal to 3 and D is equal to 1. So, we can get the solution from this set, and that means the coordinates with respect to given ordered basis is 6, the coefficient of the first matrix 6, A is equal to 6, B is equal to minus 5, C is equal to 3 and D is equal to 1. So, the coordinates are 6, minus 5, 3 and 1. So, this example illustrates how to find coordinates with respect to given basis. Now, change of basis. For this, let us consider V is an n dimensional vector space and it has 2 ordered bases as S and T. Then V belonging to the vector space V has coordinates C1, C2, Cn with respect to the basis T. So, we can write down V, and now I am using a notation in which I say V and then subscript T, that means V with respect to ordered basis T. This is C1 W1 plus C2 W2 plus Cn Wn, because W1 W2 Wn is a basis for T. Then you can express V S also, Vs in terms of V1, V2, Vn. Now, the question is, what is the relationship between the coordinates of given vector with respect to the basis S and T? Now, this describes the change of basis. Now, let us consider the vectors wj belonging to V with respect to ordered basis S is a1j, a2j, anj, because wj also belongs to V. So, we can write down its coordinates wj with respect to S as a1j v1 plus a2j v2 plus anj vn, and then Vt can be written as C1 times Wj plus C2 times W2 plus Cn times Wn. So, this is what we have written. So, Vt is expressed as this. Now, if the coordinates of vector V with respect to basis S be C1 dash, C2 dash, Cn dash, then V with respect to basis S will be C1 dash V1 plus C2 dash V2 plus Cn dash Vn, and then this is equal to what we have written earlier, C1 A11 plus C2 A12 plus Cn A1n times V1, V2 and Vn, linear combination of V1, V2, Vn, this we have written earlier. And this means in the vector form we write down the coordinates of C1 dash, C2 dash, Cn dash as multiplied by the matrix into this column vector C1, C2, Cn, which is the coordinate of the vector V in T. So, in the matrix form this equation is Vs is equal to a matrix Pst. This is a special notation we use for change of coordinates Vt. Now, this matrix Pst is defined as a transition matrix from the basis T to the basis S, and column vectors of transition matrix is the coordinates of W's in the ordered basis S, and this is what we have. We have a vector V in the vector space V. This is the representation in the vector S, which is has basis V1, V2, Vn. We have another basis T. It has W1, W2, Wn as this is the ordered basis for T. Then this is the transition matrix. So, this relationship, how we represent this vector in terms of T and this the same vector in terms of the ordered basis S. So, this is what is to be discussed, but more detail I will be discussing in my next lecture. Viewers, towards the end of this lecture I will summarize what we have done today. We have started with direct sum, and I have given you some results related with this, that is dimension of u plus dimension of w is equal to dimension of u plus w plus dimension of u intersection w. We have discussed complementary subspaces, we have then come to ordered basis, we have discussed coordinates, and I have started discussion on change of basis, but I will continue this in my next lecture. Thank you.
Thank you.